Assalamualaikum and good morning to all viewers. Today, our group from Group 6 with Title 2 will present about our project. So, our team consists of 4 people, which is the first one is Varshavel, FB24018, and then Nur Azrin Afia, FB24019, Nur Firza Hayati, FB24020, and lastly, Muhammad Shahmi bin Shaharuddin, FB24021. For the introduction, kinematic is basically the study of motion without looking at the forces that cause it. It focuses on things like position, velocity, and acceleration to help us understand how objects move over time. In this project, these principles are used to design and analyze a solving mechanism in a simple mill. The mechanism takes the rotary motions from an electric motor and converts it into the back and forth motion needed for the saw blade. By analyzing the movement and the geometry of each link and joint, we can better understand how the mechanism behaves, especially in terms of velocity and acceleration. This helps ensure smoother motions, improve efficiency, and reduce mechanical stress. To support this, the mechanism is modeled in Autodesk Inventor, and its motion is simulated using the Graphical Integrated Mechanism or GIM.
Assalamualaikum, my name is Muhammad Shami bin Shaharuddin. My metric number is FB024021. So I will explain for methodology part. First is mechanism description. The solving mechanism converts the rotary motion of an electric motor into a controller horizontal reciprocating motion of the saw blade while keeping it in a fixed horizontal position. The system consists of a motor driver crank, a vertical offset link, a connecting link, a guided slider, and the saw blade. Next part is working principle. The electric motor rotates the crank at a constant angular speed of 50 radians per second. As the crank rotates about its fixed center, it drives the vertical offset link, which transfers motion to the inclined connecting link. This connecting link is attached to a slider that moves along a horizontal guide, causing the saw blade to move back and forth while remaining horizontal. Next is motion characteristic. One complete rotation of the crank produces one full ellipsoproting cycle of the saw blade, consisting of a cutting stroke and a return stroke. The stroke length depends on the crank radius, connecting link length, and offset distance. The blade reaches maximum velocity near the center of the stroke and maximum acceleration near the reversal point. The kinematic characteristics are analyzed using simulation software and motion graph.
Good evening, sir. So I am Marcel Murgaya, FB24018. I am from Group 6 and I would be presenting the GIM software simulation. So the simulation is done through the GIM software. So basically what we have to do is create the diagram. So I did the diagram myself. So it's very basic actually doing the diagram. You just have to select the actuators actually and place each coordinate at your preferred coordinate that you have selected, and basically you just have to connect the points and you will get this diagram. And once you get the diagram, you have to go to the results and you have to click the top there, which is something called the play button, and you will play the one actually rotating. But before that, there's some steps where you have to create also the midpoint, and there's also a circle that you have to put at the top so it rotates around that. So that's what you have to do for this. And to show you the motion, wait, let me show you here. So that's the motion there that you've seen just now. So it's not very clear, but since my laptop can't screen record, that's the best that I can do. So that's the full rotation in one cycle, and beside that it's all the graphs where it shows the velocity and acceleration also. So that's what we got from that. And now the theoretical calculation part. Okay, so I'll be doing the theoretical calculation part, also explaining just a simplified version of it. So basically, the theory calculation part, we have to start by finding out all the values first. So we are given the motor's angular velocity, which is 50 radian per second, and that's the velocity that's the angular velocity that's been given in the question lah. So that's pretty easy. And after that, there are some relationships that also we have to find out. Where there's this one equation where WM equals to WD where the motor pulley and the drive pulley are connected by a belt, and we assume there's no slipping. The linear belt speed is the same on both pulleys. So that's what that equation is equal to. Then after that, to calculate the drive pulley angular velocity, we use a formula called WD equals to WMRM over RD. So that's the formula where the values are 50 times 3 divided by 6, you get 6.28 radian per second. Now, the radiuses were randomly given, where the motor pulley radius is 3 inches and the drive pulley radius is 6 inches. So that's what was randomly chosen by the group. So we got the answer for that. And after that, for the okay, after that there was we used the cosine sine rule for to get the equation where there's a n equals to 30 over sine 130 minus theta equals to 5 over sine theta. Now to find n, we put there is sine in bracket 30 sine 130 minus theta over 30. Okay, now we can actually simplify the version where sine 180 minus theta is actually sine theta. That's in the rules where you can just simplify that. So that's pretty simple. Now we have to calculate the initial and final velocity of all the this one. Wait. Okay, now the initial and final velocities. Okay, the initial and final velocity, the conditions. Okay, now at the start of motion, the saw blade is at rest. At the end of each rotation, it comes back to rest, reversing in direction. Okay, so now with this we can know that initial and final velocity is 0. It's 0 meter per second square. Okay, now the acceleration part. Okay, hold on, where's my screen? Okay, the acceleration part is actually quite easy. So acceleration, we know that a equals to v over t. So acceleration equals to velocity over time. So the velocity we got is 0.628 over 2.5, the seconds. So what we got is 0.25 meter per second square. Okay, now we assume that the acceleration is 3 meter per second square. So positive is during the forward motion and negative is during the backward motion. So that's what we got from the answers. And now to find the angular acceleration of the crank. Okay, now this one is actually quite hard, but we found out eventually. So a is the angular acceleration equals to 3 over 0.1. So 3 is the acceleration and r is the radius. So 3 over 0.1 equals to 30 radian per second square. So that's the angular acceleration of the crank. Now after that is all actually pretty simple actually. Wait, hold on. Okay, after that we got the final angular acceleration, all of that done. Now when starting motion is actually positive and when stopping is actually negative. That's why you see we put two answers right there. And now hold on, why is this bugging out? Okay, after that you see as a conclusion we put the table there where there's all the values right there. So the component, the motor shaft, crank, saw blade and drive pulley. So the angular velocity and angular acceleration. So as you can see, all our values are simplified right there. So 50 radian per second for the angular velocity of the motor shaft. Angular acceleration of the motor shaft is 0. The crank has angular velocity of 6.28. The angular acceleration is 30 radian per second square. Saw blade has 0 for both. Drive pulley has 6.28 radian per second angular velocity and angular acceleration of 0. If there's no slip occurs. If there's slip occurs, the value will change. So that's all from me. I'll pass on to my next teammate.
So for now, I will explain about velocity and acceleration analysis. First, I will talk about acceleration. So for the acceleration, is the mechanism begin with a very small positive initial velocity, as shown in the velocity graph. This indicates the slider does not start abruptly, but instead transitions smoothly from rest. Such a gradual start helps prevent sudden jerk in the system. Additionally, the straight and uniform slope of the velocity profile suggests consistent and steady motion throughout this stage, which is ideal for applications requiring stable and uniform performance. Next is velocity. The velocity graph indicates that the slider initially moves with a very low positive speed, showing that motion begins gradually rather than abruptly. This smooth initiation allows the system to shift from rest in a well-controlled manner. Furthermore, the uniform slope of the velocity curve reflects steady and reliable movement, which is essential for mechanisms that demand consistent and even output.
Assalamualaikum. My name is Nafisa Hayati binti Muhammad Salihi. My ID matrix is FB2024020. So today I want to explain about the CAD design that represent the saw blade. So first we have the crank, which is a rotating component attached directly to the power source. Then we have connecting rod, a rigid link that transfers motion from the rotating crank to the sliding component, enabling the conversions of rotational motion into straight line motion. So next we have slider, a linearly guided part that moves back and forth along the fixed path. This component carries the saw blade and performs the cutting actions. Lastly, we have a frame or a base, which is a stationary support that secures all components in proper alignment. It houses the crankshaft and provides a guide for the slider's linear motions. This mechanism converts of a rotating crank connected to a connecting rod, which in turn drives the saw blade back and forth. So the conclusion is this project successfully engineered a song link mechanism by utilizing GIMP software and Autodesk Inventor to convert rotary motions into a precise 3-second reciprocating cycle. Through rigorous kinematic and dynamic analysis, the design was optimized to minimize vibrations and mechanical stress while ensuring even force distribution for enhanced durability. Ultimately, the project demonstrates a high-level integration of theoretical principles and simulations tools to create an efficient, reliable motion control system for real-world applications.